Hi, it's time for another math easy solution. Time to discuss further into applications of integrals and further into moments and centers of mass. Now go over example 2 of the example series, and now we'll look at this example which states find the center of mass of a semicircular plate of radius r. So this is basically like my last video. I went over the derivation for just a general plate or region, finding the moment centers of mass, and now it's time to put those integrals that we derived into practice. So let's try to find the center mass of this. Let's just graph this out first, and what we'll do is, if this is xy axis, let's try to make it the simplest graph we can place this semicircle. So this is a semicircular plate, so that would be basically, let's make the center point like this. So let's make it like this. This is so that the full circle, let me try to draw a full circle around. Let's try one more time. Okay, let's try one by half, like that. Yeah, so basically we draw it like this so that it's a semicircle, and then this is dashed line representing if you had the full circle. And the reason we are doing this is because, so this would be the origin, again has a radius r. So at this is r, at this point is r, this is negative r, then here is negative r on the y-axis. So if this is the plate we're trying to find the center of mass, and the reason we write it like this is so that we have, well, this equation of a circle. Yeah, so we know the equation of a circle, that's why we're placing it at the very center, so we get the simplest equation of the circle. So recall equation of a circle, which is simply, and this one here is x squared plus y squared equals radius squared. So what we have here, when we solve for y, we get y is equal to, we'll move this x squared to this side, minus x squared, then we square root, but then y could be positive or negative, so we have plus or minus square root r squared minus x squared, and then the bottom half, this one is the minus part, minus x squared, and then what we have at the top is the positive part of that equation. So that is our equation. That's why we place the origin and place this the semicircular on the xy axis with the origin right here. So that we can have this equation, which is simpler than moving it anywhere else. So which is the plus side of the square root r squared minus x squared. And now we could just apply the formulas that I derived in my last video. So recall the centers of mass formulas. So centers of mass, or I mean center of mass formulas. Write this a bit neater. Formulas. So in my last video I derived that when you have a region like that, that the center of mass for the x, so the center is going to be, I'll go center is at the point x and y like that, and then what we'll have is where x, the center point at the x direction, or on the x-axis, I mean the x variable basically is going to be equal to 1 over area of that region, and then integral from, in our case, negative r to r of the region, and then x, f of x dx. And then y, we get 1 over the area, and then this negative r to r, then we have this 1/2 f of x, and then squared dx. Yeah, so we have these two formulas, and then what we end up having is, well, we know the area is going to be of that semicircle, that's going to be area of a full circle, pi r squared divided by 2, and that's just, and again you can see the proof of this in my earlier video for the area of a circle. So then that's this a for both of the sides, and we know obviously y equals to f of x, which equals 2 r squared minus x squared. Now we could plug this inside here, but also what we'll notice is that this finding the center of mass on the x variable, well, we could actually solve that by symmetry. So basically using the principle of symmetry, which I went over in my last video, we can easily find that, so we don't need to actually integrate principle. So by using principle of symmetry, and we know that, well, we obviously have, let's draw that plate again. The thin plate looks like this, x, y. It's something like that, which is, let's draw this like that. And it's symmetric about this line, so this is the y. So that is our line of symmetry. So that it's reflected across on both sides, so this is the same area as this, basically exact same thing. Let's draw this a bit more like it. I think that's closer to it. So anyway, so that means then that the center of mass has to be on this y-axis. So center of mass, you could just look at it, it will be somewhere around there. So this is our center of mass, x like that, where if it's like that, then the center, the x variable has to be 0. So the center of mass is basically 0 and like that, and y. So we just need to find the y form. We just need to solve the y integral formula. So thus, we know this one is equal to 0 by using symmetry, which I explained in my last video on the derivation of the formulas. So we don't need to actually solve that integral. So now we just need to solve this one, y, center line y, we'll put this called center line. So what we have is, this is going to be 1 over area, integral from negative r to r of 1/2. Make sure I added the 1/2, yeah I did. So 1/2, and then we have f of x squared dx, which equals 2. The area again is, this is pi r squared, area of a circle, divided by 2 because it's a semicircle. And then we could just take this 1/2, put it over, let's put it like this. And this is times, I'll just move this 1/2, it's a constant, move it up here. And the reason we're doing that, just put it like this, because we already have a 1/2 at the bottom, we could just cancel those. So this is negative r to r, and this is square root r squared minus x squared, all squared dx. So this 1/2s cancel, and then we just have 1 over pi r squared integral from negative r to r. And now this square root cancels with the square, or the power of 2, so we get this r squared minus x squared dx. And also one more simplification, what we could do is basically recall that the integral from negative a to a of f of x dx is equal to, well, 2 times integral from 0 to a of f of x dx. This is if f of x is even, meaning it's the same on the positive or negative side, or even, or otherwise meaning basically f of negative x is equal to f of x. For example, yeah, basically if you were to graph it out again, so something like this, x, y, if you had a function like this, I'll just make it a straight like this. Let's say that's our f of x, and this is a, then this is like that, and this is negative a. Basically we could just go 2 times integral from 0 to a as opposed to finding it from negative a to a. So something like that where it's symmetric on it, it's basically equal to left side and right side are just symmetric by this y-axis. So in our case, if g of x is equal to r squared minus x squared, which is what we're integrating right here, yeah, right above here, so r squared minus x squared, and again you notice that it's an x squared, so then if we had g of negative x, put that inside, we get r squared minus negative x squared, which equals 2, this is just r squared, and this negative x squared is going to be positive x squared, doesn't change anything, so which equals 2 g of x, yeah, so that's just g of positive x, so thus this is even. That's an even function. You can learn more about even and odd functions in my earlier video in the video link below. So what we have now is the integral of this equals to the integral, this is 1 over pi r squared. And now we have this negative r to r. We'll just go from 0, so we'll add a 2. So we're multiplying by 2 now, and then go from 0 to r of r squared minus x squared dx. So now this will just make the integration slightly easier. So now we could just integrate this. This is 2 over pi r squared. R squared is going to be integral of that is just r squared x. That's just a constant. Integral of x squared, that's just going to be x cubed divided by 3. Now it's from 0 to r. This equals 2 pi r squared. Evaluating it, let's put this r inside, we get this r cubed minus r cubed over 3. Now when you put in the 0 there, that's just 0, so just ignore that. So we have this, let's just multiply by common denominator, which is 3 over 3, so that we get 2 pi r squared, and then we have this 3 minus 1, which is 2, times by 2 r cubed over 3. So this r squared cancels with this r cubed getting an r, and this becomes 4, so what we end up getting is this equals 2, this y value of the center of mass is equal to 4 times r divided by pi times 3. Or let's write this a bit better. So 4 over 3 r pi. I'll just again write this all in one line. So 4r 3 pi is our center of mass. So so thus our center of mass is center of mass is equal to at the point 0 and 4 r 3 pi, and that is our answer. And now we could just write that into our point right here. Let's just go up all the way here. So it would be somewhere here. You just have to solve it, and this is it's gonna be a bit below from the exact center of these two because this is bigger area at the bottom. So that center line right here is 0 and 4r 3 pi. I'll call it C. So center like that. I'll be center of mass right here. Let's put a C. Okay, so that's the point right there. Anyways, that's all for today. If you learned from this pretty useful example, this example on finding center of mass, and also on using the fact that it's an even function, we don't have to integrate. So basically using some shortcut in the integration process, as well as the basically the principle of symmetry, and as well as the even function in simplifying an integral and writing it in simplifying the intervals of the integral. In this case, negative a to a, I'm negative r to r going to 0 to r, like here. Anyways, that is all for today. If you learned from this video, and like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.